So next is decimal to binary encoder. So in a decimal to binary encoder, we know that we have 10 decimal numbers, that is I9 to I0. These are the decimal numbers we have. And in order to code this, the largest number in decimal, largest one digit number in decimal is 9. So in order to code that, you need 4 bits. So output will be 4 bits and input will be 10 numbers, 10 bits. Okay, so that is an encoder. So we'll write it in the easiest way. Input and output will be, say, y3, y2, y1, y0. So input can be I0, I1, I2, I3, I4, I5, I6, I7, I8, I9, and output will be 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1. So don't continue because in decimal you have only till I9. So don't write till 15 because then that won't be decimal. So in decimal you have only from I0 to I9. So if you write it till I15, then that will be hexadecimal. Then you can write the equations for y3, y2, y1, y0. So y3 will be I8 plus I9. Y2 will be I4 plus I5 plus I6 plus I7. Y1 will be I2 plus I3 plus I6 plus I7. Y0 will be I1 plus I3 plus I5 plus I7 plus I9. And you can draw it using OR gates. So this is decimal to binary encoder. Yes. So now suppose you want to convert binary to decimal. Okay. So if you want to convert binary to decimal, what is it? So binary to decimal, you want to convert binary to decimal. Okay. So decimal, you know, has 10 numbers, and binary, how do you represent? These 10 numbers you can represent in binary from 0, 0, 0, 0 to 1, 0, 0, 1. Okay. Just like we saw in decimal to binary. But when you represent these numbers in binary, more than one bit is high. In the case of an encoder, you can have only one bit as high at a time. And when you write decimal, you can have only one bit as high at a time. Right? So binary to decimal is not an encoder, it is a decoder. And decimal to binary can only be a encoder. Binary to decimal can only be a decoder. Yes. Likewise, binary to anything. Binary to octal, binary to hex. All these can only be decoders. Right? So Suppose you have something else, that is you want BCD to, or say binary to XS3. Okay. Binary to XS3 means binary also you can have more than one bits high at a time. XS3 also will have more than one bits high at a time, right? So in that case it is neither a encoder nor a decoder. Such circuits are called as code converters, just like that. Okay, those are code converters, one code to another code. You don't have the rules like you can have only one bit high in the input, you can have only one bit high in the output, nothing like that. In the case of code converters, any code can be converted to other code. Okay, so in such cases they are just code converters, they are not encoder or decoder. But then like you don't have the n to raise to n, those rules existing, they are just code converters. So binary to XS3 will be XS3, if I'm taking just 4 bits, then input also 4 bits, output also 4 bits. Suppose my input is I3, I2, I1, I0, and my output is say, since it's XS3, I'm writing it as X, X3, X2, X1 and X0. So 0, 0, 0, 0, that will be 0, 0, 1, 1. This can be taken as binary or BCD. Both are the same only. Okay, binary to XS3 or BCD to XS3, it's the same. So this will be like this. 2 will be 5, 3 will be 6, 4 will be 7, 5 will be 8, 6 will be 9, 7 will be 10, 8 will be 11, and 9 will be 12. So 12 is the largest number you can represent using 4 bits in XS3. So you have to stop here. So that's why I told that this can be taken as either binary or BCD. This can be BCD or binary. Either ways it's the same thing. Input and output is XS3. Likewise, you can do like gray, binary to gray, gray to binary. Okay, those are also code converters. And then you can write the equation for the outputs. How will you write the equation here? In this case, you don't have the rule like only one bit is high, nothing like that. So you'll have to write the K-map for x3, x2, x1, x0, solve it, and then draw the truth table. Okay. You can do binary to gray or gray to binary. Both are code converters, 4 bits each. Yes. So that is the difference between encoder, decoder and code converters. Suppose you need construct suppose 1 by 8 demux using 2 1 by 4 demux ICs. In this case, you can make use of the concept of strobe which we used in multiplexer. Okay, so in demux it is called an enable, not a strobe, and this is an active high signal. In the case of multiplexer, it was strobe, that is in the case of mux, it was strobe, and it was an active low signal, that is you give a low, that IC gets enabled. In the case of demux, it's called same thing, it's called an enable. What was strobe in mux is called an enable in demux. It was active low in mux, it is active high in demux. Okay, so unless and until it is specified that it is active low or active high, you can take it either ways. Just say that I'm taking it like this, but in lab it is like this because that's how the ICs are made. Okay, so in practical ICs this is how it is, but in theory if you just assume then that's fine. So how do you do this? You can just have a 1 by 4 1 by 4 demux will be 2 select lines. This is kept at 1, this is also kept at 1. This input is anyways 1. Okay, so I'll give the A here, when A is okay, A is 0, when A is 0, this is made active. When A is 1, this is made active. This is E, enable. Okay, so you have to give A to the second demux. So this is my 1, 0, 1, 2, 3, this is 4, this is 5, this is 6, and this is 7. Right? So when A is 0, BC is 0, then O0 is output comes at O0. A is 0, BC is 0, 1, then it comes here. because this particular IC is not selected, because when I is 0, this particular IC is not active. Only the first IC is active. Yes, so that is how it is. In the case of mux, we gave A directly to the first IC because we wanted A to be 0 to make the first IC work. Here the enable pin is active high, so you are giving A to the second IC because when A is 0, you want this to be inactive and you want the first IC to be active. So A bar is given to the first IC. Yes. So that is how you construct a bigger demux from smaller demux ICs. So likewise you can construct any circuit you can take up a question like design a half adder using 2 2:1 mux ICs. You have two 2x1 mux ICs. Yes, this is what you have, and what you need is A, B, sum, carry 0 0 0 1 1 0 1 1 0 0 1 0 1 0 1 1 sorry 0 1. So this is what you need. So how do you implement this? Using this. So when you get a question like this, first you should place whatever you have with you. Okay, you have two 2x1 mux ICs. So this much you drew. What do you know? You want a half adder. So you need the truth table of a half adder. So that you drew. Okay. Now you should try to connect between this particular truth table which you need and the ICs which you have. Okay, and you have strobe. So how do you connect these? So half adder means you need two outputs, so you have two outputs. Suppose this is my sum and this is my carry. So where do I give A, where do I give B? How do I get all these? So you can think about this as an SOP. So SOP how? So sum is a function of AB equal to sigma m 1 2, and carry is a function of AB equal to sigma m 3. Now you can implement this particular SOP using this. How? This is my sum IC, this is my carry IC, both have AB, that is the common thing. So in this particular case, the problem is that you have only one select line for these, but you need two select lines here because both sum and carry both are a function of AB. So where do I give this A? I'll have to give the A to the input. So how do I give that? So for that, what we should do is we'll have to simplify this. We'll have to make the 4x1 mux into 2x1 mux like we did previously. So how do we do that? So if I take, I'll have to take separately, that is I'm eliminating A. or I'm taking A and eliminating B. Suppose I'm eliminating the LSB. So A0 means S is B. A1 means S is B bar. So for sum, so when A is 0, S is B, and when A is 1, S is B bar. A is 0 means the first line, A is 1 means the second line. So A is 0 means sum is B. So here you have B, and A is 1 means it is B bar. Here it is B bar. So that is sum. So in the case of carry, if it is carry, it was like this. So A is 0 means it is 0, and A is 1 means it is B. So A is 0 means it is 0, and A is 1 means it is B. This is B, and this is logic 0. So that is how you get the half adder using two 2x1 mux ICs. Yes. So A0, B0 means A0 means this is selected. Here A0 means this is selected. So B, A0, B0. So sum is 0, carry is also 0. A0, B1 means A0. So the first line is selected. B1, B1 means sum is 1, carry is 0. A1, B0, A1 means the second line of both the ICs are selected. So A1, A1, B0. So B0 means sum becomes 1, and here it becomes 0. A1, B1 is A1. So second line is selected. B1. B1 means here it is 0, sum is 0, and carry is 1. So that's how you design a half adder using two 2x1 mux ICs. You can do the same with full adder, half subtractor or full subtractor, any of these. You can also design a half adder using two 4x1 mux ICs, 4x1 mux ICs without simplifying. You can try that. Design a half adder using two 4x1 mux ICs. It can be half adder, full adder, half subtractor, full subtractor, using 2x1 mux ICs or 4x1 mux ICs. Yes. So